This lesson is on gas stoichiometry. It's a way to use the gas laws that we've been studying to determine the quantities of different gases involved in chemical reactions. So Avogadro's principle is the principle that allows us to do this. The Avogadro's principle states that the partial pressures, volumes, and number of moles of gases in the same container and at the same temperature are proportional to the reaction coefficients. So that's a lot of words. It doesn't make a whole lot of sense when you first hear that. So here is a reaction, and what it's saying is that you have 3 molecules of hydrogen gas reacting with 1 molecule of nitrogen gas to produce 2 molecules of NH3 gas. Now, I know when you first start studying chemistry that this is just an awful lot of numbers and letters and symbols, and it can get really confusing. So what it's actually trying to tell you is that we have 3 of these things reacting with 1 of those things to produce 2 of those things. Now, things is not a very scientific way of talking about that. So instead, we're going to use X. We're used to using X. So we have 3X is reacting for the hydrogen. And we're going to replace nitrogen with 1X. And then 2X is going to be for the NH3. So in example A, we see that 2X equals 2 atmospheres. So I'm going to write that off to the side. And I think that's probably the hardest part when you first start doing this, is getting that there is an equal sign that goes between the X's at the top and the numbers that you have at the bottom. So let me see, I'm going to erase that because it's... All right, so it says the final partial pressure of ammonia, NH3, is 2 atmospheres. What were the partial pressures of the nitrogen and hydrogen that reacted? So if 2X equals 2 atmospheres, that means that 1X, the nitrogen, would be 1 atmosphere, and 3X would be 3 atmospheres. So the math is really easy. It's the concept that people have a little bit of trouble with. All right, so let's go on to another example. So example B, 90 liters of hydrogen were used. How many liters of nitrogen were also used? And so we write down the number with the quantity that it goes with. That's probably the biggest mistake that people make. So we have 90 liters of hydrogen. So we're going to write 90 underneath the hydrogen. So 3x equals 90. So we're going to divide by 3 so we can get what 1x is. And when you're solving these problems, that's usually a good strategy, is to always go back to what the 1x is and then go from there. So 1x is 30, and then 2x would be 60. And then our third example, now we're going to do moles. Remember, you can do pressure, you can do volume, and you can do moles. So it says 5 moles of ammonia were formed. How many moles of nitrogen and hydrogen were used? So we have 5 moles of NH3, so 2x equals 5. So we're going to go 5 divided by 2 to get what 1x is. So that's 2.5 moles. And then we take our 1x and multiply by 3, which gives us the 7.5 moles. All right, staying with the same reaction, we have another example. It says the final partial pressure of ammonia is 1 atmosphere. How many grams of hydrogen were reacted if the reaction is done in a 1-liter flask at 25 degrees C? All right, so that's a lot of information. Let's do the easy part first, and let's convert from partial pressure of ammonia to partial pressure of hydrogen. So we just write down the number. So 2x is equal to 1. So we're going to divide by 1x, and that will give us what the nitrogen is. So that's 0.5. And we'll write that in there. Whoops, I've got the wrong one. So this is 0.5. So we want to get 3x, so 3 times 0.5 is 1.5. All right, so now we have the pressure. We have the, no, that's not pressure. We have the volume of the flask, and we have the temperature of the flask. So we can use the ideal gas law in order to figure out what the number of moles is. And then once you have moles, you're almost all the way to grams. So we have the ideal gas law, Pivnert. Fill in the numbers. So we have 1.5 atmospheres worth of hydrogen gas. It's in a 1 liter flask. There's our gas constant. Convert the temperature into Kelvin. So 298. And you get that it is, the number of moles of hydrogen would be 0.0613 moles. So now we want grams. So we're going to go moles times the molar mass, GFM, to get grams. So 0.0613 times 2.01, it should be 2.016. I'm not sure why it says 5. And you get 0.124 grams of hydrogen are actually needed for this reaction. So that would be, if you were trying to do this reaction, it would be a way for you to figure out how much hydrogen gas you would need to measure out. All right, so this is actually from the worksheet that goes with this lesson. It's called Flatulent Moles, Gas Stoichiometry. It's a joke. So the first thing you have to do, we have an unbalanced chemical reaction equation, so we have to balance it. So we start out with the hydrogen, and we see that we're going to need to have these coefficients. So 1, 2, 1, 2. And then we look at the example. It says we have 2.5 liters of methane, which is CH4. Wants to know how many liters of carbon dioxide will be formed. So we have 2.5 written underneath CH4. And we're trying to figure out how much CO2 will be formed. That's why I have it in the yellow box. So we set up our x's, our proportionalities. So it goes 1x, 2x, 1x, 2x. These numbers are just the coefficients that are in front of the substance in the reaction equation. So if you look at this, we say, all right, we got 1x equals 2.5, so over here 1x is still 2.5. Next part of it, it says how many liters of oxygen are needed to react with the methane. So we're trying to figure out oxygen now. So that would be 5 liters. And we want to know how many liters of water vapor will be formed. And so that's also going to be 5 liters. All right, so the next one is just another example. So same reaction, different numbers. So you have 2 atmospheres of CH4 are reacted with oxygen. It wants to know what the pressures of carbon dioxide and water vapor will be separately after the reaction is complete. So we write down what we know. So you have 2 atmospheres of CH4. So that means it's going to be 2 atmospheres of CO2 and 4 atmospheres worth of water vapor. And then the last part would be how many atmospheres of oxygen will be needed to react. And so we say, all right, well, that's a 2x. That means it's still going to be 4 atmospheres. And that is it for this lesson. It goes pretty quick. So thanks for listening.